Section 3 focuses on the ideas of variability and relative standing. So we're going to continue our conversation about descriptive statistics and how we describe data. In the last section, we began this discussion really with the measures of central tendency, where we calculated the mean, median, and mode. So we're actually going to continue with that same example we looked at in the last section. So here it is. Suppose that we take a random sample of 8 fuel-efficient cars and record the gas mileage. Calculate the following for the results. So this is our data. We have 8 data points. So we're going to talk about first calculating different measures of variability. So variability is basically a measure of how spread out your data is. So it's most common to give 2 measures: a measure of center, which tells you where the center of the distribution is, and then a measure of dispersion or variability, which tells you how spread out the data values are. And there's different ways to measure the spread of the data. I'm going to start with something that we're probably all familiar with. I like to talk about this just really because it's not a very good measure, but it's something that you'll hear people throw out there a lot of times. So I really like to start with this idea of just a range. So a range is a simple idea. You just take the highest value minus the lowest value in your data set, and of course that will give you the range. So the highest value in this data set is 45. The lowest value in this data set is 33. So the range is simply just the high minus the low, which gives you 12. So let's talk about what's wrong with the range. The biggest issue with the range is what it's based on. We're trying to measure the spread of the data. So if you just think about this, what if you have 1,000 data points in your data set and you use the range? Well, if you think about that, really all you're doing is picking 2 of 1,000 data points and using only those 2 values in order to determine how spread out the data is. That doesn't make a lot of sense. And on top of that, if you think about the 2 values that you're picking, the 2 values that you're picking are the most extreme values in your data set. So if you have really extreme values, it really can inflate the range. But you're picking the 2 most extreme data points in your data set, and you're saying these 2 values are going to give me a good measure of how spread out the data is. And that's just not realistic. Lots of times people report the range because it's simple to calculate, but it is not a good measure of dispersion in general. Now, I will say if you have a perfectly symmetric distribution, the range is actually not a bad measure. But the way it works in statistics really is anytime you have a perfectly symmetric distribution, pretty much everything works. But when you deviate from that, which we pretty much always do because it's very rare that when you collect data you get a perfectly symmetric distribution. So when you deviate from that, lots of these measures aren't very good. The range is one example of that. Anytime you have an entire data set and you're picking the 2 most extreme values in order to create a measure, it's probably not a very good measure. So let's talk about what we really do use in statistics. We use this idea of the sample variance and sample standard deviation. So we're going to start with the idea of the variance. These 2 go together. You have to calculate the variance before you can calculate the standard deviation, as you should know from your reading in the notes. But let's start with the idea of the variance. So what the variance does is the variance measures the average squared distance the data points are from the mean. That's what it does. The average squared distance the data points are from the mean. So we're referencing the mean, and it's a good method because the mean is the center, and we're basically looking at how far the data points are from the mean. So let me show you the formula. Here's the formula for the sample variance, and there's a few different versions of this formula. First, we denote the sample variance by s squared, and the squared represents the fact that this is in squared units. It is not in the same units as our original data. We're measuring the average squared distance the data points are from the mean. So it's squared distance, and I'll talk about why we do that here in a minute. So the way we do this mathematically is we take what's called the sum of the squared x's. We abbreviate that SSX. So SSX stands for the sum of the squared x's. Sum of squares is something that we deal with a lot in statistics, especially if you move forward and take more advanced statistics courses. Sum of squares is something that you manipulate and deal with all the time. So if you divide that by n minus 1, then you get your variance. The sum of the squared x's, if you look at that second version of the formula there, the sum of the squared x's is simply equal to the sum of the quantity x minus x bar squared. That is what the sum of the squared x's is equal to. So let me just talk a little bit about that. We call that the conceptual formula of variance. It is conceptual. It's based on the definition. So if you think about the definition, you could almost come up with that formula. We said it's the average squared distance the data points are for the mean. So remember that x is your data values, x bar is your mean, n is your sample size. And of course the capital sigma is our sum signal. If we take each x, so we take our x and we subtract x bar. That's what's in the parentheses, right? We take each x, we subtract x bar. That gives us the distance the data value is from x bar. Then we square that. That gives us the squared distance the data value is from x bar. And then if we sum those, and you would think you would divide by n, and you actually do if it's the population, but in a sample, in order to make it unbiased, we actually have to divide by n minus 1. We won't go into all the theory behind why that is, but it basically makes it unbiased. The deal is once you calculate one statistic, remember the variance is based on the statistic x bar. So once you calculate one statistic, you actually only need n minus 1 data points in order to have all the information from the data set, because you already know the mean. If you have n minus 1 data points plus the mean, then you can always figure out the last data point. And mathematically, the way that works is once you have calculated a statistic, you're calculating another one based on that, then the denominator basically becomes n minus 1. And I'm not going to go any further into that, but that's essentially how it works. When you base a statistic on another statistic, your denominator changes. So that's just the definition. One thing I want to mention is, why do we square this? Why in the world would we want to find the average squared distance? Why not just find the average distance? Well, the deal is, if you think about this, if you take that squared off of that formula and you just take the sum of x minus x bar, well, the deal is when you take an x and you subtract x bar, some of the x's are going to be below the mean and some of the x's are going to be above the mean. By definition, the mean is the center, right? So if you take a value below the mean and you subtract the mean, you're going to get a negative quantity. If you take a value above the mean and you subtract the mean, you're going to get a positive quantity. And because the mean is the balancing point, if you just sum all of those negatives and positives together, they will always balance out and you always just get 0. So we can't do it like that. So basically we have to make everything positive. So one way to make everything positive would be to use absolute value. But if you've ever dealt with absolute value mathematically, you know that it's not very fun to deal with. So instead, what we decide to do is we square it. So when we square these values, it makes them all positive, and then we start with the average squared distance the data points are from the mean. That is the variance. That last formula there is the one that we should use when we calculate variance by hand. I call that the computational formula. It is the formula that we will actually use. So let's just go through the process of showing that those two formulas are equal. So let's start with the manipulation of the sum of squared x's. So this is a very common manipulation. We've already said the sum of the squared x's equals the sum of x minus x bar quantity squared. So let's simplify that. So here's where we don't have any data, but we have to use our properties of sums. And the way that these manipulations tend to work is they all tend to go down kind of the same process. The first thing that you always do with these kinds of scenarios is you always, if there's anything that you need to simplify within the sum, then you do that first. And then you basically separate out the parts. You can sum each part. That's one of our properties. And then we deal with constants. And our constants, of course, is our other property, our other properties. And then once you deal with constants, then you simplify and you have your simplified version. So in this case, we want to manipulate the sum of squareds so that we basically we want to write it in a simpler and really different form. The thing that we don't like about the sum of squares when you do this by hand, which is why we don't use this as the computational formula, is when you calculate x bar lots of times is like some big long decimal. And if you take every x and you subtract this big long decimal, it's either going to be a mess or you're going to have to round. And when you round every value and then you square it and then you sum all of those, you just compound your rounding error when you square and then you sum. So you end up with a bunch of rounding error in your outcome. So in order to get rid of that issue of all that rounding error, we come up with this computational formula, which we're getting ready to show is algebraically equivalent. So the first thing we have to do here, of course, is we have to square that thing out. So if you square it out, it looks like this. If you basically just use FOIL, x minus x bar quantity squared is you take x and you square it. Then you take minus x bar, but there's two of those, so that's minus 2 x bar x, and then plus x bar squared. So all we did there was basically use FOIL in order to square out that quantity. So now once we have this squared out, then we can start to use our properties. So remember, with the sum, you can sum each part. So we can rewrite this as the sum of x squared minus the sum of 2x bar x plus the sum of x bar squared. Remember, you can always do that with a sum. It doesn't matter the order that you sum in. Summation is commutative, so you can sum in any order. A plus b equals b plus a, as we talked about before. So we can basically sum each part of this and then do the other operations. So now we are ready to start dealing with our constants. So that first term doesn't have any constants in it, so it's just going to stay the sum of x squared. Now the second term, of course, 2 is a constant, but here's the other thing you have to realize in these kinds of problems, is once you calculate x bar and you use x bar to calculate the variance, x bar becomes a constant because you've already calculated it. So x bar is the sample mean, and it becomes a constant. So remember that in that second term there, you can pull the constants out front of a sum. So we end up with 2x bar, that's our constant, times the sum of x. In that last term, the only thing we have is an x bar squared. We've already said that x bar is just a constant. And remember our property, when you're summing a constant n times, you just get n times that constant. So that last term just works out to be n times x bar squared. So now we've used our properties, we've simplified this pretty well. Now it's just a matter of just finishing up the simplification, just using some algebra. So the last thing that we kind of have to do here before we really simplify is we have to deal with the fact that we have this x bar in there. Because x bar, we can rewrite x bar. Because we know that x bar is the sum of x over n. Everything else is written in terms of sum of x's and n. So what we want to do next is we just want to rewrite that x bar in terms of its definition, which is x bar equals the sum of x over n. So if we do that, notice it's exactly the same as the previous step. The only difference is everywhere you see an x bar, the x bar is simply just replaced by what it is, the sum of x over n. So now we can start to simplify. So that first term is not going to change. It's going to stay the sum of x squared. There's nothing we can do with it. That second term, we have sum of x over n times sum of x. So we have 2 sum of x. So that means we have sum of x squared over n. That last term, you'll notice that we basically have sum of x squared in the numerator because when you square that, you get sum of x squared over n squared. But we also have an n out front. So that n out front is going to cancel with one of those n's in the denominator, and that just leaves us with sum of x quantity squared over n. So now we have like terms. If you look at those last 2 terms, you'll see that both of those have that sum of x squared over n. So we basically have minus 2 of those plus 1 of those, which just gives us minus 1 of those, which gives us sum of x squared minus sum of x quantity squared over n. So that's a very common simplification. It's the simplification of the sum of squared x's. That's something that we do a lot. We use this different version of the sum of the squareds. So for the sum of squared x, you can of course write it as we originally wrote it, that sum of x minus x bar quantity squared. But we also now should know that that is mathematically equivalent to the sum of x squared minus the sum of x quantity squared over n. So we're going to now actually manipulate the variance formula. So this is just what we just proved. We just proved that the sum of squared x equals the sum of x squared minus the sum of x quantity squared over n. Okay, so now let's go back to our variance formula. So the variance formula is the sum of squared x over n minus 1. Well, we just simplified the sum of squared x, and we're just going to replace that sum of squared x with what we just simplified it into. So notice it's the same formula, other than I just replaced sum of squared x using our simplification that we just completed. So now in order to finish this up and actually get your computational formula for variance, it's actually pretty straightforward. The only thing we really don't like about this formula is we don't like that it's a complex fraction. We don't like that we have that in the numerator of this, we have a fraction within that numerator. So we want to get rid of that n in the numerator. So one way to do that would be to multiply through by n. Of course, you can't just multiply through by n because that would change the formula. But what we can do, and it's a little algebra trick that you should all know, is we can just multiply by n over n, because n over n is like multiplying by 1, so it doesn't change the outcome. Because when you multiply 1, you get whatever you started with. So I'm just going to take this formula and just multiply it through by n over n. And when you do this, it works out really well. You distribute the n, and that first term just becomes n times the sum of x squared. In the second term, we get minus, but the n's there just cancel, so all you're left with is the sum of x quantity squared. And then in the denominator, you just have the n times n minus 1. And if you look back up at the variance formula, of course, you will see that that is the computational formula for variance. So that is our proof. That allows us to know that these formulas are equivalent. So whenever we use this computational formula for variance, we know it's going to give us the same answer as the conceptual formula. It actually looks more messy, but it's actually way easier to do by hand to use this computational formula rather than the conceptual formula because of what I mentioned earlier about the decimals. So this one has none of those issues. It's actually pretty straightforward to use this one by hand. So we don't do a lot of these algebraic manipulations, but you got to be able to manipulate things algebraically. That's one of the things that we do in here. So you got to be able to use these properties of sums, which is why we spent time on them in the last section. You got to be able to use these algebraic properties of sums to simplify. So that is an important idea, and it's something that lots of students aren't real familiar with, so it's something that you want to make sure you understand these properties and how to use them, especially when you don't have data, because you can't just do what we did in the last section and just list out your data in columns and figure things out. Here you actually have to manipulate things algebraically. Okay, so let's go back to our example, and let's calculate the variance. So in order to calculate the variance, we basically need two different sums along with our sample size. So we know that n in this case is 8. If you remember from the last section of notes, we already figured out the sum of the x's was 301. But as I mentioned when we talked about sums, lots of times when you calculate statistics, you need also the sum of the x squareds. And this is the first time that you really see that. But in order to calculate variance, you need two different sums. You need the sum of the x's, but you also need the sum of the x squared. So you got to have both of those quantities to calculate variance. So if you look at your variance formula and you plug things in, this is what it's going to look like. So that is our computational formula for variance. And you can see all we did was plug things in. And of course, hopefully you see where those sums come from. That 301 is just the sum of your x values. Then we have the column that is the x squared values. You just take each x and you square it, and then you sum that column. So if you'll notice, when we plug things in, we plug in 8 for n. That's the first thing you see in the equation. Then we have the sum of the x squared. So the sum of the x squareds, the squared is inside the parentheses there, which means we square by order of operations before we sum. So you square the values, then you sum them. That's what that 11,435 is. We squared the x values, then we summed those x values. So you'll see that first term is 8 times 11,435. Then we get minus, In that next term, you'll see the sum of the x in parentheses, which means we take the sum of the x and then we square that quantity. So that's what you see there at the end. We take 301, the sum of the x's, and we square it. And then the denominator, of course, is just n times n minus 1. So that's just 8 times 8 minus 1. And of course, remember that n is just your sample size. It's how many x values you have. So then we can just simplify that. And I don't always show every single step, but here I do. If you go through each step, if you take 8 times 11,435, you'll get that 91,480. 301 squared is 90,601, and then you get over 8 times 7, that gives you 879 over 56, and that will give you 15.696. Please use at least 3 decimals. That's what I typically use, is 3 decimal places when I need to round, and that's what I use here, so you get that 15.696. So one thing to notice about variance, it's in squared units, so it's not very easy to interpret the variance, which is the thing that we don't like about the variance, is it's difficult to interpret. Let me just mention one other thing before we talk too much about that, though. One thing to think about with variance is, remember, variance is a squared value. So one thing to think about is if you ever get a negative variance, that means that you did something wrong. The variance can never ever be negative because it's a squared value. So if you ever calculate variance and you get a negative, you know you made a mistake somewhere. Technically, variance can be 0, but it's only going to be 0 if all your data points are exactly the same, because that means there would be 0 variability. So the only way the variance will be 0 is if, like, you have a data set and every data point is a 3. Then you would have 0 variability. Otherwise, the variance is going to be some positive quantity. But as I mentioned before, it's in squared units. So that's what you got to be careful of, is it's hard to interpret. So we don't like the fact that it's in squared units, so we want to basically get rid of the fact that it's in squared units. And that's where the next measure comes in. We call it the sample standard deviation. The sample standard deviation is simple once you get the variance. The sample standard deviation is just the square root of the variance. So since the variance is the average squared distance the data points are from the mean, the standard deviation is the average distance the data points are from the mean. And in this case, the standard deviation will give us that 3.962. And what that tells us is that these data points are on average about 3.962 units away from their mean or their center. The center is usually measured with the mean. This is the value that we typically use. This is the value that we interpret. We typically report the mean, which is the center, and then the standard deviation, which tells us on average how far the data points are from that center. So these are important quantities. The variance and standard deviation are something we use a whole lot in the field of statistics. The other thing that we will sometimes do with standard deviation, and this becomes really important as we get into inferential statistics, is we also will use standard deviation as a unit of measure. So we use standard deviation to measure variability, which is a very important component, but we also, in inferential statistics, start to use it as a unit of measure. So one of the things that you will see a lot of in a statistics class is you'll see a lot of this idea of a z-value or a z-score. So let's suppose that we look at the x value of 45, just one of those x values, and we want to find the z-score. The way you find the z-score is you always take the observation, you subtract the mean, and you divide by the standard deviation. So there's actually a bunch of different z formulas in statistics, and there's some other formulas that look very similar to z formulas, but they all have the same form. It's always observation, subtract the mean, divide by standard deviation. And as we get into inferential statistics, you're going to see me use that pattern a lot. Observation minus mean divided by standard deviation. That's a good pattern to get down. So here, our observations or our outcomes are our x values, right? So we take our x, we subtract the mean of the x's, which is x bar, we divide by the standard deviation of the x's, which is s. So for example, if you want to calculate the z-score for the value of 45, as you can see, you just simply take 45 minus the mean, which we calculated in the last section. It was 37.625. And then we divide by the standard deviation, which we just calculated, which is 3.962. That will give us a z-value of 1.861. So what the z-value tells you is it tells you how many standard deviations the observation is away from the mean. So in this case, what this z-value tells us is it tells us that this x value of 45 is 1.861 standard deviations above the mean. We know it's above the mean because it's a positive value. If it's a negative value, that means it's below the mean. But the z-value tells you how many standard deviations an observation is above or below the mean. Let's just do one more that's below the mean, just so make sure we're on the same page. If you want the z-value for an x value of 35, then you just do the same thing. In this case, we will get negative 0.663. So you'll see that when a value is below the mean, that means you're going to get a negative z-score. So your interpretation is pretty much the same. The big difference is now you're talking about below the mean instead of above. So we would just say 35 is 0.663 standard deviations below the mean, and that's how you interpret those. So as a descriptive measure, z-values simply tell you how many standard deviations an observation is above or below the mean. These are useful in comparing when you have things that are measuring basically the same thing, but they're scaled differently. It gives us a good comparison. You can calculate the z-value for each one, and then you can compare them. Like if you want to compare if you want to compare a math ACT score to a math SAT score, then you could calculate the z-value for both, and you could compare those two z-values to see which one was higher. Now, you wouldn't want to do this in some situations because you are assuming that the group of people who take the ACT and SAT are similar, which might be a reasonable assumption, which would probably be a reasonable assumption in that case. And it's also a very large group of people. When you have really small groups of people and the groups are different and you compare z-values, that doesn't make a lot of sense because, remember, z-values are relative to the other people who take the test or whatever you're measuring. So you do want to make sure that if you're comparing z-values from two different groups, that the groups are similar. The other thing that we will utilize standard deviation for in terms of a unit of measure here at the beginning is we use it in the idea of the empirical rule. The empirical rule is just a general rule for any mound-shaped distribution, and we don't really say that this is mound-shaped, but it's a pretty mound-shaped distribution if you look at the data set. So if you have a mound-shaped distribution, meaning it's not, meaning it can be symmetric or it can be skewed, but it's not like uniform where it's flat. It's also not bimodal where it has multiple modes. So whenever you get into uniform or bimodal distributions, the empirical rule doesn't work very well. But most of the time it works really well. It's just a general rule that tells us about how much of our data is within 1, 2, and 3 standard deviations of the mean. So the general rule is this. If you have a mound-shaped distribution, we know about 68% of our data is within 1 standard deviation of the mean, about 95% is within 2 standard deviations, and about 99.7% is within 3 standard deviations. So essentially what we do here is if we want to know about 68% of our data will fall within the interval, then you just simply take the mean and you subtract the standard deviation, and you take the mean and you add the standard deviation. We typically write this in interval notation because that's what it is. Within this interval is about 68% of our data. So here, the mean, of course, is 37.625. The standard deviation is 3.962. So if we work this out, we'll take that 37.625 minus 3.962. That'll give us the 33.663. And then we take the 37.625 plus 3.962. That'll give us 41.587. And within that interval, we can be confident that's where about 68% of our data lie. Like I said, that works really well for mound-shaped distributions. And of course, these percentages are always going to be the same. So you can calculate other percentages, but we won't talk about how to do that until later in the class. So for now, if I ask these kinds of questions, it's always going to be 68%, 95%, and 99.7% because that's what the empirical rule gives us. If you go out to 95%, that means you're getting almost all of your data. So it's very unusual to get an observation that's more than 2 standard deviations below or above your mean. 95% of your data is within 2 standard deviations. You can see the majority is within 1 standard deviation. More than half your data is within 1 standard deviation. And most of your data is within 2 standard deviations, 95%. So to get this interval, we do basically the same thing. We just, instead of subtracting 1 standard deviation, we just subtract 2 standard deviations and we add 2 standard deviations. So it works the same way. So you just take basically 2 times your standard deviation and you subtract that and then you add that. In this case, we can be sure that about 95% of our data is between 29.701 and 45.549. If you go out 3 standard deviations, then you really almost get all your data. You get 99.7% of your data. So it is super unusual to get a z-value that is beyond 3. And this is a good reference. Like 95% of z-values are between -2 and 2, right? Because it tells you how many standard deviations you are above or below the mean. 68% of z-values are between -1 and 1. 99.7% are between -3 and 3. So if you ever get a z-value of 12, you should always look at that because that is a really unusual z-value. Now, it can happen that you get a z-value of 12, but it is super, super unlikely for that to ever happen. So there's usually some reason why that happens, and those are always indicators that you should look at that value and see what's going on. Why in the world is that thing 12 standard deviations above the mean? So for this one, we just simply take x bar minus 3s and x bar plus 3s. So same thing, we just subtract 3 standard deviations. So we take 3 times the standard deviation, and then we take 3 times the standard deviation, and then we subtract that and we add that. And I didn't show you all the steps here, but here we just end up with 25.739 to 49.511. Okay, the last thing that we talk about in this section. So we've really focused on the idea of standard deviation and really the idea of variability. That's really the key thing in this section. But the other thing that's important is we also want to talk about some ideas of relative standing, and we will use these some. It's important to have an idea of what a relative standing value is. So you should have read this in the notes, but you should have an idea of what the 5-number summary is. The 5-number summary basically is the 3 quartiles along with the low and the high. The 3 quartiles, of course, divide the data set up into 4 equal parts, and then we add the low and the high, so we have endpoints for that lowest 25% of our data and that highest 25% of our data. So in order to do this, I just have the x values listed out there to the right like we have before. So the x values are in order, which is of course important here. So when you do the 5-number summary, you always start in the middle and work your way out. So the 5-number summary consists of the 3 quartiles, the low value, and the high value. So always start in the middle and work your way out. So start with Q2. So Q2 is the same thing as the median. So we actually, in the last section, already calculated the median for this data set. The median is 37. There are 8 data points here. So all you do is just find the median. That gives you Q2. That's always your starting point. So notice, since there's 8 data points, we have 4 data points below the median in rank order, and we have 4 data points above the median. So even though there's 2 values of 37, technically the median is in between those 2 middle values. So lots of times I'll just mark that as the median, just in between those 2. Since there's an even number of data points, there's that 37 in between those 2. So to get Q1, so all we do is we look at the lowest 4 data points. So we have 4 data points that are below the median, 33, 34, 35, and 37. So those points that are in that bottom half, the bottom 4 values and the top 4 values is how we split this in half. So if we just look at those bottom 4 values, we have 33, 34, 35, 37. To get Q1, we just simply take the median of those 4 values. So that means 34 and 35 are in the middle. So we just average 34 and 35, and we get 34.5. That gives us Q1. And then we do the same thing for the upper half of the data. The upper half of the data is 37, 39, 41, 45. So the two middle values there out of those four is 39 and 41. So that gives us a Q3 of 40. And that's the way we do this. The way you find the quartiles is you always start with the median. The median is not part of the lower half or upper half if you have an odd number of data points. You just circle it and don't include it. When the median is not a data point like here, then you just divides it in half. And you separate, the median separates it into two halves, the lower half and the upper half. Q1 is then just the median of the lower half, and Q3 is the median of the upper half. It's really that simple. Then we add the low value. The lowest value is 33. The highest value is 45, and that gives us the endpoints. And this is what we consider our 5-number summary. When I say identify each part, by the way, I mean identify what the low, Q1, Q2, Q3, and high are. And then, of course, to find the 5-number summary, you actually give the values. So that's what I'm looking for there. One other thing that we sometimes talk about, and I like to talk about a little bit, is what we call the interquartile range. So the interquartile range is actually a measure of dispersion. It's a measure of variability, just like the range was. It's actually better than a typical range, but it's still not as good as the standard deviation, which is what we most commonly use. But the interquartile range is nothing more than the range of the middle 50% of your data. So if you take Q3 minus Q1, in this case, that'll give you 40 minus 34.5. That will give you 5.5. That is what we call our interquartile range. The nice thing about the interquartile range as compared to a typical range is you're not dealing with extremes. When you look at a typical range and you're looking at the high and the low, well, those are likely extreme values. At least they're the most extreme values in your data set. So the nice thing about the interquartile range is it kind of knocks off those extremes, and it gives us still a measure of variability, but it's not totally based on extremes. Like I said, it's still not as good as the standard deviation, but it is something that you see when you look at a box plot, which is what we're getting ready to look at. So I do like to make sure that you understand what the interquartile range is, and you should know what it is and be able to calculate it. Okay, so these quartiles, a lot of the reason why we talked about these is so we can look at this graph. But this is a box plot, and there are 3 different boxes here. I actually just added a couple other data sets with the fuel-efficient cars, but that first box you see there on the left is from the data that we've been using. So let me first just mention where the box comes from. So the box itself the box itself basically represents the interquartile range. So when you look at the box, the bottom of the box will be at Q1. The top of the box will be at Q3. So for our data set, the box on the left, you can see there at the bottom, it says fuel efficient cars. That's the one that came from the data set that we've been using. So you'll see that the bottom of the box, I know the scale is not super accurate, but if you look at the bottom of the box is actually at 34.5, which is what we said Q1 was. The top of the box you can see is right at that 40, and that is what Q3 is. The top of the box is at 40. So that box itself represents the interquartile range. The line that goes through the box is your Q2 value or your median. So in our case, the Q2 was 37. So if you look at that line in that first box that goes through, you'll see that that line basically lines up to 37. So when you look at the box, you're just simply looking at the bottom of the box is Q1, the line that goes through the box is Q2, and the top of the box is Q3. We then have the lines that extend from the box. The lines that extend from the box are called the whiskers. The one at the bottom goes to the lowest value. So the lowest value in our data set was 33. So if you look at that bottom whisker, you'll see that it goes down to about 33. The whisker at the top represents the top 25%, and it goes up to the highest value, which you'll see the top of that is at about 45. So when you look at the box, you're really looking at the 5-number summary. The bottom of the bottom whisker is the low. The bottom of the box is Q1, the line through the box is Q2, the top of the box is Q3, and then the top of the top whisker is the high value. The only exception to that is when you have extremes, which I'll mention here in a minute. But that's what a box plot is. Okay, so let me give you the typical things that I would ask with a box plot. So in this case, it's obvious, but just one of the examples, or one of the things that I commonly ask is, which one typically is higher or lower? So here we have 3 different kinds of cars. We have fuel-efficient cars, we have other kinds of cars, and then we have SUVs. So you can see those along the x-axis there at the bottom. So which one had the best gas mileage? And of course, you would know that without even looking at the graph, but obviously the fuel-efficient cars have the best gas mileage, right? So the way that you tell that, based on this box plot, if it wasn't obvious like it is in this case, is you would look at 2 things. You look at the position of the box, and notice the box for the fuel-efficient cars is higher than for the other cars and for the SUVs. So it's higher on the y-axis, which means typically those vehicles get better gas mileage. The other thing to look at is the median. The median is also higher. That is the line that goes through the box. Both of those things are higher, which tells us the fuel-efficient cars get better gas mileage. No surprise there. But the things that you look for when you're comparing what typically happens is you're looking at the position of the median and the position of the box. Another thing that I will ask is variability. For example, I might ask, which one of these vehicles has the least amount of variability? Well, when you're looking at variability, you're looking at how spread out things are. So if you're looking at how spread out things are, then you want to look at how big the box is and how long the whiskers are. If you look at how big the box is, you can see that the other cars, the middle box, the box is smallest. The whiskers are also fairly small there. So in this case, we would argue that the other cars, that middle box, has the least amount of variability. So when you talk about variability, you're looking at the size of the box first, and then the length of the whiskers. Smaller boxes mean less variability. Shorter whiskers mean less variability. So lots of times I'll ask which category has the most or the least variability. Another thing that I will ask is about outliers. So do keep in mind that not all data sets have outliers. This one does have one outlier. If you look at the SUVs, you'll see that dot down there at the bottom. It's at around 11. That dot represents an outlier. So when you look at a box plot, outliers are always, depending on the software used, outliers are always represented by a dot that's like separate out there or an asterisk. So if you don't see any dots or asterisks that are separate from the whiskers, then there is no extreme values. The nice thing about the software is it'll determine whether or not there are extreme values. And it will identify those as either a dot or an asterisk depending on how or what kind of software you use. When you have an extreme value, like the lowest point in the SUV data set is 11, but notice the whisker stops before that. So when you have an extreme value, the software will determine it is extreme, and it'll put a point there, and then the whisker will just go to the next highest value. So that's what happens to the whisker if you have an extreme. The whisker just goes to the first value that is not an extreme value, and the extreme values are represented by dots or asterisks. So there is one extreme value here. It is with the SUVs. And then the last thing is the shape. So when you determine the shape of a distribution with a box plot, we typically turn them on their side. Make sure you turn it the proper way. And whenever you do this, at least mentally, we don't necessarily turn the computer on its side, but we kind of mentally turn the graph to its side. It's easier to determine the shape that way. Make sure you turn it clockwise because you want to make sure that that gas mileage number line there is increasing from left to right. And if you turn it counterclockwise, then your number line will be going backward, and that's not what you want. So you want to make sure you turn these graphs clockwise so that your real number line is going the right way. So let's just go through these. Let's just start with the middle one first because it's the easiest. If you look at the middle one and you determine the shape of the distribution, that one's simple because the box is exactly symmetric. The things that you look for, you look at the position of the median in the box. The position of the median in the box is if it's in the center, that indicates symmetry. If it's not in the center, that indicates you have skewness. The length of the whiskers. If the length of the whiskers are the same, that indicates symmetric. If they're not the same, that indicates that you have skewness. So the middle box, the median is right in the middle. The whiskers are the same length. So everything there tells us we have a symmetric distribution. So that middle box, those other cars would be considered symmetric. Let's look at the fuel efficient cars. So notice with the fuel efficient cars, the median is not in the middle. The median is actually left of center. And the way I like to think about this is think about which side of the box is bigger. And you'll notice the top or the right side of the box is bigger than the left side. So be careful how you interpret this. That does not mean there's more data to the right. Remember, exactly half your data is to the right of the median and half the data is to the left. But what that does mean is it does mean that the data to the right is more spread out than the data to the left. And when the data to the right is more spread out, and you think about that like in a histogram, that means you're going to have a longer tail to the right. So because the right side of that box is bigger than the left side, that indicates you have a right skewed distribution. The other thing you should look at, of course, is the whiskers. The whisker in this case to the right is also longer. And since the whisker to the right is longer, that also indicates a right skewed distribution. It indicates the data to the right is more spread out. You have a longer tail to the right. So for the fuel efficient cars, you definitely have a right skewed distribution. For the SUVs, you have just the opposite. The median is right of center, meaning the left side of the box is bigger. Also, the whisker to the left is longer, meaning you have a tail to the left. So everything there indicates you have a tail to the left. So the SUVs would be a left skewed distribution. Now, I'm not worried about you determining whether or not something is uniform or bimodal. We're not worried about that. But I do want you to be able to look at a box plot and tell me whether or not it's symmetric. And if it is not symmetric, which direction is it skewed? Is it skewed to the right or is it skewed to the left? I will say that sometimes you can get contradicting information in a box plot. Sometimes you can get a box that shows right skewed and you can get whiskers that show left skewed. I won't do that to you on a test or anything. But if you ever were in that situation, then what you would want to do is you would want to look at a histogram and you would want to compare the mean and median. Keep in mind, this is only one method that we use in order to determine shape. We have multiple methods to determine the shape of a distribution. This is just one of them. When you're really determining shape, you're going to want to look at multiple things. You're going to want to look at maybe a box plot, histogram, compare the mean and median. All these things together are going to allow you to make a really good decision about what the shape of a distribution is. And that's it. That wraps up section 3. So section 3 talks about variability and relative standing, and that is the end of section 3.